Hello, this is my presentation. My presentation is about data preprocessing and modeling workflow. To begin with that, this project focuses on classifying advanced liver using clinical and laboratory data. A comprehensive pre-processing pipeline was implemented to ensure data quality and model robustness. Mixing values in numerical features was filled with a zero, while categorical features were input using placeholder category. The original four-stage outcome variable was transformed into a binary target, where stage 4 was labeled as a positive classes and stages 1 to 3 as a negative class, reflecting a clinical meaningful decision boundary. To improve feature distributions, we will use the equivalence. Skewness was evaluated for all numerical variables, and log transformations were applied to highly skewed features. Outliers were identified using the inner quarter range, IQR method, to treat it with winsorization to limit the influence of extreme value. Categorical variables were encoded use one hot encoding and a clinical relevant subset of features such as bilirubin, uh, alumini, and a platelet count was selected for modeling. The dataset was split into training and testing data sets using an 80/20 holding strategy, standardized and balanced using SMOTE to address class imbalances. Next part is modeling approaches and module sustainability. Actually, two modeling strategies were explored in this study. First, decision tree classifier was implemented within scaling pipelines that included standardization and SMOT sampling. The decision tree achieved an accuracy of approximately 63 on the test set. Despite its moderate performance, the model offers strong interpretability, making it particularly variable in medical contexts, where transparent decision rules are essential. Decision trees also neutrally capture nonlinear relationships between clinical indicators and disease severity, making them an appropriate baseline module. Second, the autonomous machine learning approach is used to H2ML, AutoML was applied. The AutoML process evaluating multiple modules under cross-validation with a class balancing enabled. The best performing module selects as a GBM, which significantly outperformed the decision tree, achieving approximately 84% accuracy and an AUC of 0.89. GBM models are well suited for structured tabular data and are particularly effective in small to medium-sized datasets due to their robustness to noise, ability to handle class imbalance, and a capacity to learn complex features interactions automatically. Insights and patterns revealed by the results. The substantial performance gap between the decision tree and JVM highlights the complexity of liver progression. The results suggest that disease severity is driven not by single biomarkers in isolations, but by nonlinear and high-order interactions among multiple psychological indicators. Variables such as bilirubin, alumni, and time together provide strong predictive signals supporting the idea that blood-based biomarkers can serve as effective for liver distancing stagings. An important insight for the analysis is potential risk of data leakage. The feature end days representing time until death or transplant showed a strong correlation with disease stage, while valid in retrospective analysis. This information will not be uh, available at the time of diagnosis in real-world clinical setting, including a feature could artificially inflate module performance, understand the importance, and temporary features validation before deployment. For the real data implications, from a practical perspective, these findings suggest that machine learning models trained on routine blood test results could support non-invasive screening for advanced liver disease, potentially reducing reliance on costly and invasive procedures such as liver biopsies. And clinical decision support systems, high AUC models like GBM could assist physicians in early risks, satisfactions, and pattern prioritizations. However, the study also emphasizes that careful feature selection and validation are critical to ensure that modules trained in experimental setting can be safely and responsibility to translate it into real-world healthcare applications.